All right, welcome back, and my sincerest apologies for the length of the last video, and that somewhat abrupt stop. It is something that is a challenge I am finding with the lecture videos. When it comes to explaining, try to develop intuition of ideas, that's a lot easier in a face-to-face setting because I can get feedback from the audience there, at least in some sense with facial reactions. Not as easy to do remotely, so I tend to just try to explain everything I can possibly think of. I will be much more cognizant in this video on the length of time. Let's do one more variance-related thing before we move on to something else. So Theorem 4.3 is going to talk about the variance now of a function of a random variable. The variance of a function g of x of the random variable x is, so the notation here, sigma squared with the subscript of g of x, just to indicate that we're talking about the variance of the function. This is, according to the definition, going to be the expected value then of g of x minus its mean, minus the mean of g of x quantity squared. All right, so again, in the same idea of just the variance and the original definition of variance, it's the expected value, it's the expected squared distance that this takes on from its mean. All right, so opening this up into the discrete or continuous cases, it's going to look like this. If it's discrete, we're going to be summing over all x values. We need the squared distances from the mean of our function g of x times the probability that we take on that value, so times f of x. Of course, that is the discrete case. In the continuous sense, naturally then, same thing, but we replace the summation with integration. Integrate. This is g of x minus its mean, squared distances, times f of x dx. That is the continuous case, of course. All right. So, with that, let me just adjust some things here. Let's take a look at an example of this. This actually isn't as bad as it might look. You might be especially concerned with the continuous sense, because that integrand is kind of nasty. Just with the way we even handled something originally, like we did this lengthy problem up here by definition. But it's actually not that bad. I swear, it's not that bad. So in order to convince you, hopefully, that I want to illustrate it with an example. So let's say x is a random variable with PDF f of x equals x squared over 3. X goes from -1 to 2, and it's 0 elsewhere. 0 elsewhere. Okay. Let's find the variance of g of x equals 4x plus 3. Okay, let's find the variance of g of x equals 4x plus 3. So in order to find the variance, we need to know what the mean is, right? We're going to need to know the mean of g of x. So first, let's make sure we can tackle that. So we get the mean of g of x here. That's the expected value of 4x plus 3, which according to the definition of expected value would be the integral of 4x plus 3 times x squared over 3 dx. All right. And I'm pretty sure we already did this, actually. Pretty sure we do that in the last video here somewhere. We did that right here. Yep, 8. We know that number is 8. So let's go ahead and just skip that computation. 8. We know that that is 8. All right, so let's use that and get the variance then. So the variance of 4x plus 3 is equal to, according to this definition, the expected value. Before you, don't go right into the integral here, though, okay? Because so if I look at the formula, the mean shows up here and here. Start with the expected value because you can simplify what's in this expected value. This is the expected value of, let's see here, it's the expected value of, what do we have? It is g of x minus the mean. So the expected value of 4x plus 3 minus the mean squared, right? Expected value of g of x minus mu, quantity squared. All right, well, that is the expected value then. 4x plus 3 minus 8, that's the expected value of 4x minus 5 squared. All right, well, this isn't that bad because now this is just an expected value problem, right? This is just going to be the expected value of, depending on how, well, yeah, maybe you can either FOIL this out if you want to at this stage, or you could put it in the integral right now, right? That is your call. This would be the expected value of, what if we FOIL this out? That would be 16x squared minus, so 4 times 5 is 20 times 2, so minus 40x plus 25. So there's our expected value, okay? All right, that's kind of nice. That looks good. And I'll mention there are some tips and tricks we can deal with later that we'll see in future videos about dealing with expected values like this. But for now, at this stage, we would just dive into the expected value computation. So we're going to integrate, according to this PDF, from minus 1 to 2. And it's going to be 16x squared minus 40x plus 25 times our PDF, which is x squared over 3 dx. There we go. And so I would bring out this 1/3 from the x squared over 3, integrate from minus 1 to 2, and multiply the 16, distribute these to there. So we're going to have 16x to the 4th minus 40x cubed plus 25x squared. And now I just got a nice polynomial there to integrate. We'll take the antiderivatives and plug in our endpoints at minus 1 and 2. It's not too bad. If you want to check your arithmetic skills, we should get 51 over 5. 51 over 5 would be the variance there. All right. So the new topic that I really want to focus on in this video then is this definition, and it has to deal with, if you sort of think about what we've been doing, talking about expectations and means. If you think about the most recent videos, we looked at the mean of a random variable, we looked at the mean of a function of a random variable, and then we looked at talking about some means and expectations of joint distributions, just briefly, right? Just a couple things you can do with joint distributions. And so you might ask yourself, is there a way you can talk about the variance of like a joint PDF in some sense? And what we can talk about, we actually don't use the word variance, but we will talk about and introduce the idea of covariance of random variables. The covariance of random variables x and y is defined to be the following. Sigma x, y is the notation. This is the expected value of, here's what the covariance is. It's the average, it's the distance that x is from its mean times the distance that y is from its mean. And that's the average of that product, okay? Generally speaking, this gets to be a little bit of a mouthful, so let's go ahead and just slowly write down the definition here. So in the discrete case, how do we get this expected value? That's going to be x minus the mean times y minus its mean. And just like we did the expected value with the joint PDF table, we multiply by the probability that x and y are that value that we get from the joint PDF. And we need to cycle through all possible pairs of x and y. And we add these together. So we cycle through all the y values, cycle through all the x values, and add those together. This, of course, is the discrete case. If your PDF is discrete, if it's continuous, it's the same idea, but we are dealing with then a double integral to get the covariance. So we'd integrate from minus infinity to infinity. X minus mu x times y minus the mu of y times the joint PDF f of xy dy dx in the continuous case, okay? Again, I want to reiterate, I have attempted to set up the online homework so that we are not dealing with double integration in the problems, because that is not a formal prerequisite for the class. So that should be avoided. These double summations can be done with a table. Maybe we'll look at an example of that. But if you come across any double integration questions, let me know right away so I can deal with that, all right? Talk about what the covariance actually means here, right? Because this is not really talking about a spread or a dispersion, if you will, okay? Because the joint PDF is a little bit harder to maybe visualize what that means in a graphical sense, all right? So let me notate this here, all right? Really, what the covariance is going to give us, what we're concerned with actually, is we're concerned with the sign of the covariance and whether it's positive or negative. The sign of the covariance indicates, this is a relationship between x and y, indicates whether the relationship between two dependent random variables is positive or negative. Is positive or negative. The relationship being positive or negative. Okay. What do we mean by being positive or negative? I like to think of it this way: a positive relationship. A positive relationship. In a positive relationship, if x goes up, y should go up as well. That is a positive relationship. In a negative relationship, if x decreases, then y decreases as well. Okay? And it's really basic. That's all it is, but it is what it is. All right? So what do we mean by positive relationships here, right? You could think of if x was the let's say square footage of a home. Typically, if the square footage of a home increases, we would expect the price y of that home to increase as well. So we would say that the square footage and the price of a home have a positive covariance. A negative relationship, this is wrong. This is wrong here. This is wrong. This is also a positive relationship. If the square footage of the home goes down, the price would go down as well. That is not a negative relationship. A negative relationship would be opposite interactions. That's a negative relationship, okay? That's a negative relationship, okay? So, for example, a negative relationship would be something like this. When the age of the home decreases, if the age of the home decreases, the price of the home might go up, right? That would be a negative. Those are opposite relationships. So positive or negative. Negative would be opposite interactions. A positive relationship means they would behave the same way. And so it could be vice versa, right? If x decreases, we expect y to decrease as well. Okay. And this is between two dependent random variables. That's because if it turns out if x and y are independent, if x and y are independent random variables, then the covariance is 0. If they are independent, the covariance is 0. And intuitively, I hope that makes some sense, because if they're independent, then increasing x, for example, doesn't affect the outcome of y. So the covariance there is 0. Now, this is a one-way street. If they are independent, the covariance may be 0. That is a one-way street. All right? If the covariance of x and y is 0, they might be independent, but they also might not be. X and y may or may not be independent. X and y may or may not be independent, all right? So think about it like this. So how can this be? If they are independent, the covariance is 0. But if the covariance is 0, they may or may not be independent. One of them is basically more restricted than the other, I guess, in some sense, right? So this is a one-way street, okay? So just because the covariance is 0 does not mean they are independent per se, right? For example, if I got a Big Mac for lunch, then I got a cheeseburger. If I got a cheeseburger, I may or may not have gotten a Big Mac. There is a difference, okay? There is a difference. All right, there's a difference. Now, like there was with variance, there is an alternative and a preferred way to compute the covariance. And that is in theorem 4.4. The covariance, typically how we'll compute it is as follows. It's the expected value of x times y minus the expected value of x times the expected value of y. Okay? Times the expected value of y. Again, this is usually how we'll compute it, but I don't like to open with this theorem because it doesn't really provide insight as to what we're measuring, whereas this original definition really helps provide the intuition on what the covariance is actually computing. But in practice, we'll compute it this way. All right? Also, check this out. This might be a little weird. What would the covariance of x with itself be? Or sigma x. Right? Well, that would be the expected value, according to this, of x times, so that would just be x times x minus the expected value of x here times the expected value of x. Well, this is the expected value of the square of x. And what is this then? Minus expected value of x. This is expected value of x. That's the mean, right? And that's so mean times the mean. That's mu squared. Well, what is that equal to? That's the variance of x, right? That is the variance of x according to theorem 4.2. According to theorem 4.2, that is the variance of x. The covariance of x, in some sense, is just a special case of, or the variance of x, in some sense, is just a special case of the covariance of x, right? Okay, so there we go. All right, let's do one example here real quick with covariance, and then maybe we'll take another short break. I want to use this definition here, so I have an example. Let's do this in the discrete case. So what are we going to do here? I'm going to make a table. How many values do I need here? So 1, 2, 3 for my y values. And then x is going to be 1, 2, and 3 as well. There's my x values, okay. And the probabilities inside here are 0.05, 0.05, and 0.10, 0.05, 0.10, 0.35, 0, 0.2, and 0.1. Let's find the covariance of x and y. Let's find the covariance of x and y. Let's see what we need here. Oh, sorry about that. Let's find the covariance of x and y. Well, we need the expected value of x, we need the expected value of y, and we need the expected value of x times y. All right. You know what? This is a good place to pause. Let's take a quick bathroom break, grab a snack. I would encourage you actually maybe to try to go through this, thinking about what we are going to need here. We need the expected value of x from this formula. We need the expected value of y. That's another computation we're going to need. And then we need the expected value of x times y as well. We're going to need the expected value of x times y. So why don't you go ahead and see if you can't get those when you're ready to come back. And then we'll go over the numbers and the answer in the next video.